So I know I said that golden ratio number 5 was going to be my last video of the series, but I thought of a few things that I just wanted to let you know. So hopefully this will be quick. So I'm in Excel and I'm just going to create something that no doubt you are all very familiar with. So I've got 0, 1, 1, and in this cell down here I am going to go with this. A1 plus A2. Now when I grab this corner and stretch it out, I get a series of numbers which you will no doubt recognize. This is the Fibonacci sequence where each term, of course, is a sum of the two previous terms. So how did I get 5? 2 plus 3. How did I get 8? 3 plus 5. How did I get 13? 5 plus 8. And so it goes onward to infinity. Okay, I wanted to show you this because this number sequence is right here in the golden rectangle. So if we can conceive that this distance right here is 1. So let's see if I can put that in. That's a distance of 1. Okay, 1 unit. Then this square has a side length of 2. Now we can see pretty easily that 1 plus 2 equals 3, and there it is right there, so 3. All right. Okay. Let's move this into place. Now, if we accept that this is a square here, this is a side length of 2, therefore this is a side length of 2. This is a square with a side length of 3, therefore this is a side length of 3. 3 plus 2 equals 5. We have a side length of 5 here. So let's put that in. Number 5. And you can kind of see where this is going. 5 plus 3 is 8, which is the side length of this square. So let's put that in. And if you're looking at the Excel spreadsheet and you're following the numbers, you're seeing that these are the numbers of the Fibonacci sequence, and they're occurring in order of basically following that golden spiral that I drew in a previous video, following it out. So the 8 would be right here. This is 8 units. This is 5 units, 8 units. So this square is going to have a side length of 13 units. So we have 13 units here and 8 units here. So 8 plus 13 is going to give us 21, which of course is right here. If this side is 21 and this side here is 13, well 13 plus 21 gives us 34. So that is the side length of this square right here. And then we can go one more time and say that if this is a side length of 21 and this is a side length of 34, then you're going to get the rectangle has an overall length of 55. Now, one of the cool things about this it's really cool, is that when we start dividing these numbers of the Fibonacci sequence, you end up becoming closer and closer to the golden ratio. So let's do the division over here in Sketchpad. So I'm going to calculate. So I'm going to start with 1 divided by 1, which is going to be very easy. 1 divided by 1 equals 1. Yeah, that's not news to us. Okay. And then we're going to go, okay, well, we've done 1 and 1, so let's go 2 divided by 1. 2 divided by 1 is 2. Hey, wait a minute. Are we not going in the wrong direction here? What's going on? All right, let's try 3 divided by 2 now. 3 divided by 2 equals, ooh, okay, getting closer to the golden ratio, maybe? Well, let's try 5 divided by 3. 5 divided by 3, I actually know the answer to this one, that's cool, that's close to the golden ratio, and let's just do a few more to see where this goes. Kind of jumping all over the place and kind of landing either side of the golden ratio and getting closer to it as we climb higher and higher into the Fibonacci sequence. Wow, that's close, isn't it? That's close. Let's do 2 more, and then we'll stop the insanity. So I need 34 divided by 21. Even closer to the golden ratio. Last one. Now, are we going to get an exact golden ratio number? We are not, and that's okay. Yeah, so we end up jumping, we start really far away, okay, we start really low and then way too high. Then lower again, lower than the golden ratio, then higher. Then lower than the golden ratio, then higher, then lower, then higher, then lower. And we keep jumping back and forth over that line, but getting successively closer to it as we divide these numbers higher and higher up. Now the cool thing is that we never actually arrive there, because the golden ratio is an irrational number, and you know, we don't have a limitless space in our calculator. We don't have limitless place value columns, and even if we did, we still couldn't accurately represent it in that way. To do so accurately, we would have to revert to the algebraic expression 1 plus the square root of 5 divided by 2. But I just think that it's really cool that this sequence, which is so prevalent in nature and in art, is connected to the golden ratio and is visible right before us in these nested squares. So that's one thing I wanted to show you. The other thing I wanted to show you kind of goes right back to the beginning here. And in the first video I showed you this line segment divided just so that this ratio is correct. But I wanted to show you something different, because what would happen if we reversed these? Okay, what would happen if I said, okay, well, what if I tried this? BC, the ratio of BC to AB is equal to the ratio of AB to AC. Would that work? Or am I just talking nonsense? Well, let's give it a whirl and see what happens. So, let's do our first side here. So we're going to go with BC, where are you? There you are, divided by AB. Okay, now some of you are looking at this saying, hey, wait a minute, that looks familiar. And it should, because 0.61803, 1.61803. Coincidence? I don't think so. I'll let you chew on that for a while I deal with this side of the proportion. So we're going to go with AB, and we're going to divide that by AC. And hopefully you've predicted correctly. Yes, the proportion still holds, it's reversed, but good question, why is it that when you reverse the values here, the result that you get is one less, exactly one less than the golden ratio? Food for thought.